Welcome everyone to our winter symposium and especially to the PC7 Proposers Day and Teaming event. I'll be joined in this presentation by my colleague Dr. Nick Morris, who is our FHE Technology Manager at NextFlex and who has put a ton of time into developing Project Call 7 along with many of our members and government partners. And so we stand here today just about a year after we were at the same point on Project Call 6. The Proposers Day and Teaming events for Project Call 6 were held last February. I'm happy to report that we have 18 projects that have been funded and are underway as a result of Project Call 6. And we're looking forward to similar successful projects coming up from Project Call 7. So what we're looking to do today is to give you some background for non-members, some background on NextFlex and our Project Call process, a bit of a refresher for our NextFlex members and those partners who have been involved with Project Calls since the founding of NextFlex. Then to present to you information that is in the Project Call guidebook. You can all find that information on the NextFlex website. We have a dedicated Project Call 7 page where you can find all of the information. And I will just point to you that information really is the source for all the information about the call. If I say anything here that contradicts that or seems to contradict that, go with that. If there's a question about it, you have many ways to contact us at proposal@nextflex.us by email. We're happy to answer any questions throughout the process to make sure that everything is clear. So, starting in, all of the work that we're presenting here is based on our contract and our cooperative agreement with the U.S. government operating through the Air Force Research Lab. All right, so we're going to talk about some additional resources related to Project Call 7. As I said, background on NextFlex. We're going to talk to you about the Project Call 7 process, the schedule, the themes, how we develop the topics, and then we'll present each of the topics. Nick will walk you through all of the 8 topics that we have within Project Call 7. We have some updates to the evaluation criteria, nothing major, really just trying to reflect better the process that has been used historically. So we've made some changes to that process, the way we communicated about it, and so we'll talk through those. And then lots of time for Q&A. We want to make sure that we're answering any questions that you have about the project call. And then we'll move into the Project Call 7 teaming event. That's an opportunity for anyone who's here in the room or who's joining us virtually to present for about 1 minute on background of their organization, what they're interested in working on in PC7. Really, it's about generating partnerships because that's so much of what our projects are about, is generating teaming across the FHE ecosystem. All right. So I've already mentioned the events, the virtual teaming event that's going to follow, the fact that the PC7 guidebook is the definitive reference for anything related to PC7, and how you can contact us with questions. We just have a screenshot on the right side here of the Project Call 7 webpage. All right, so background. All right, I think as you all know, NextFlex is one of the now 16 manufacturing innovation institutes that are spread across the country focused on different areas of technology and manufacturing, dedicated to enhancing U.S. manufacturing competitiveness and advancing the technologies in their respective spaces. 9 of those institutes are funded by the Department of Defense, of which NextFlex is one. We've been in existence since 2015 when our cooperative agreement was established with the federal government. We are based here, for those of you in person, here in San Jose, California. For those of you who are remote, we're still based in San Jose. We have about 105 industry and academic members from around the country, as well as many government agencies with whom we work. We say more than 20, depending on how you divide that up. It's probably a number much greater than 20. We had a first cooperative agreement that ran from 2015 and is actually just wrapping up at this point now, with a core federal funding in that agreement of $75 million, much of which was dedicated to funding projects, and an additional cost matching from our members of $96 million, and that's industry, academic organizations, and state governments contributing that cost matching. And in addition, we did more than $41 million in agency-driven projects through that cooperative agreement. We are now happily in the second cooperative agreement phase of the Institute, which began last year and runs through 2027. It has a core funding of only $27 million, so reduction with a matching cost share of $27 million, but it has a much higher ceiling of $100 million, actually recently increased by $150 million, so $250 million agency funding ceiling for that agreement. And actually, many of our project calls are funded through mechanisms that rely on that agency-driven project funding now, including the core project calls that we'll be talking about today. They're funded through a project that came in as an agency-driven project. So what is FHE? It's really important that we have a common definition and understanding of what we mean by FHE as we start into one of these project calls, so everyone's thinking about it the same way. And so we really describe FHE as being the intersection of this additive circuitry, the additively manufactured electronics, with conventional components, so things like passive devices or integrated circuits, to create functionality that is greater than either of them could produce together, produce form factors that were previously unavailable, and just to be able to carry out operations that we couldn't do before. We include the term flexible in the definition, in the name, flexible hybrid electronics, but as Malcolm said about an hour ago, we really think much more about the field of hybrid electronics, because flexible is just one characteristic that these devices may include, but it is not a mandatory element. We also think about all additively manufactured electronics. We think about conformal electronics, conformable electronics, and 3D printed electronics. All of that is in our definition of FHE, and anything in that space would be relevant to Project Call 7. So really our vision for NextFlex is to bring together these disparate industry sectors into one unified, high-performing ecosystem for FHE, and to do this across the US to ensure our manufacturing competitiveness. We want to accelerate the development of the technology, accelerate the deployment of FHE manufacturing in the US, and in doing that, make sure that we are establishing a robust workforce for FHE. All of this comes down to transitioning technologies into products, into manufacturing, and that's both on the commercial side and the defense side. All right, I've mentioned our 105 or so members across the country. That membership is broken into 3 tiers, plus an observer tier. Those exist on both the academic and the industry sides. Our membership is about 3/4 industry at this point, about 1/4 academic. We used to say it was about 1/3 academic, and the change here really just reflects the growth in the industry membership, not any kind of reduction. It's actually a growth in academic members, just perhaps a little slower than the industry growth, which I think really reflects the transition of the technology, the maturation of the technology from something that was sort of pre-commercial into something that is commercial now, so greater industry involvement. We also think about the importance of having all of the different elements of the ecosystem involved in the institute and in projects. So that's the design and manufacturing companies, the equipment companies, OEMs in the industrial and aerospace or medical or other end-use areas. Research organizations, I won't read through the whole list, but all of the different areas, materials and semiconductors involved in generating these projects and identifying what the field needs and in moving us forward. We have, as I've mentioned, government partners from across many different agencies, many different fields of government, and different areas of application and technology and ways that they participate with us. NextFlex is focused on the middle range of manufacturing readiness levels and technology readiness levels. 4 to 7 is really our mandate when it comes to these project calls. So the idea being to go from something that has been proven out, it's not pie in the sky, it's not a sketch on a napkin that somebody thinks maybe will work. It's been shown, it's been demonstrated, it has the ability to be made, but that needs maturation. It's not yet able to be produced commercially. Our goal is to help move things farther along and closer to being able to be produced commercially. So MRL 4 is titled Breadboard and Manufacturing Process in a Laboratory Environment, out to MRL 7, so prototype system and subsystems in operation and production environments. So this is not commercial production, but it's getting much closer to commercial production capability. That's matched by the technology readiness level maturation as well. This does not mean, from a Project Call 7 standpoint, that every project needs to start at 4 and end at 7. In fact, it would be highly unlikely that a project would go from 4 to 7 within a 1-year time frame with the type of investment that NextFlex is able to put in. So projects may start above 4 and move up. They may start at 4 and move to something like a 5 or a 6. That would be perfectly reasonable and acceptable. Likewise, they may not move above 7, So they may start at 6 and move to 7. It's possible that a project doesn't transition in MRL within the timeline of a project, but just simply matures and addresses the really the important elements that help it to get partway from one to another. That could be acceptable as well. So when we ask you in your proposals to identify what is the current manufacturing readiness level and your plans within the project, what we're asking for is a reasoned and realistic assessment of what that MRL is and what that TRL is, and explain to us why the work that's being done is important and relevant. It's not a scorecard. It's really identifying that it is an appropriate type of project for Nextflex to be investing in, and that the investments are going to result in meaningful improvements to the capabilities. So I'm not going to go through all the details on this chart, but there's a relationship between MRLs, manufacturing readiness levels, and technology readiness levels, TRLs, that exist. Your MRL can't exceed your TRL, for example. Later in the week, actually, for Nextflex members, on Thursday, we have a session during the Tech Council meeting that will focus on MRL and TRL assessments, because we really want to help elevate the capability of our membership in doing those assessments. They're a valuable tool in running projects and in assessing how you progress. So that's a member-only session. It's not necessary. It's certainly not needed for a Project Call 7 proposal, but it's something that I do want to call your attention to, and we can talk about that more. From the Project Call 7 website, we have links to MRL and TRL documentation information for those of you who may not be terribly familiar with MRLs and TRLs. All right, now let's get into more details of Project Call 7. Really, all of that has been background information so far. All right. As Nextflex develops project calls, it's an industry and ecosystem-driven process. We start with our technical working groups, which are made up of our industry, government, and academic members, and certainly advised by our Nextflex technical staff. We start by road mapping the FHE space, identifying what are the current capabilities, the current gaps, and needs, and then prioritizing those gaps to identify what are the most important advancements for the field. So we do that across our technology platform demonstrator groups and our manufacturing thrust area groups. We combine those together and produce a prioritized list of gaps. We then go out and we solicit ideas from the community for topics that we'll solicit within the next project call. The idea is to align the ideas that come in against the gaps that have been identified and prioritized, and select topics that will be the most relevant for the community. We look for cross-cutting areas of importance, as well as the very specific gaps. In a little while, we'll talk about the approach that we've taken to defining Project Call 7 topics, which has been to create broad topics. And so these encompass those priority areas. They align to them, but they allow some freedom for proposers to be able to identify the projects that they would like to do to have near-term business impact and improve the likelihood of technology transitions into manufacturing, for example. We go through the process where our technical working groups identify topics, and members at large can identify potential topic ideas. We combine them, we massage them, we explore them, try to identify how we can sort of broaden or narrow the topic depending on the suggestions that are made. And then we bring a set of topics to our technical council to vote to advance those topics, maybe in some cases to narrow them down to a smaller number, which then go to the governing council, the tech council and governing council both being made up of our industry, academic, and government members. That is what determines the topics that have gone into Project Call 7. All right, the process, as I mentioned, starts with road mapping and topic development. We publish the guidebook, that's the gray box on this chart, and we then move so we've published that was a week ago, we published that on the 22nd of February. We're now entering the phase where all of you will be writing proposals. Unlike standard government proposals, we can interact with you during the proposal phase. And we highly, highly encourage this. These are what we call pre-submission consultations. In years past, we had a two-stage proposal process where white papers were submitted, they were reviewed, there was feedback provided, and some of those white papers were invited to full proposals. That was the first phase of the process back in those old days of how we provided feedback on ideas and tried to improve the quality of the proposals that would come in. A couple of years ago, we changed that up. We wanted to accelerate the process. It's important to have these projects get underway as quickly as possible to have the fastest impact we can have. And so one of the ways we did that was to eliminate the white paper stage, shorten up the proposals a bit so that they would be less of a time commitment to writing a full proposal, having not been narrowed down previously. But we added this pre-submission consultation phase. And I was really happy that in Project Call 6, we had a very high rate of usage of that pre-submission consultation. It's not mandatory, but as I said, it's highly encouraged. The whole point of that process is the way that process works, you identify that you want to have one of them. You tell us what project topic it's for. In one of the appendices to the guidebook, we've provided a list of questions. It's based on the Heilmeyer Catechism from DARPA, adapted to the kind of projects that we do. You fill that out. It's about 11 or 12 questions that you just answer. They could be a sentence in some cases, maybe no more than a paragraph. We're asking for 1 to 2 pages max of information. This is just you helping us to know what conversation we're coming into. And then we'll meet with you. You'll tell us about your project, proposal, your ideas. You'll tell us the challenges you have. Maybe you have a partner that you need on the project that you haven't yet identified. We can help give you some suggestions for what the project should include, maybe a partner to consider bringing onto your team. Whatever it is you need, the whole point of that consultation is to improve the quality and the competitiveness of your proposal. The meeting is not a part of the evaluation criteria. Information on that meeting will not be given to the reviewers. It's just an opportunity for you to get some feedback and some thoughts. Everyone benefits from them, NextFlex members and non-members alike, and so I would encourage all of you to take advantage of that. It's just a part of the proposal development phase. Proposals get submitted. They're then sent out for peer review, and that peer review process we'll talk about toward the end of this Proposers Day session. It's outlined in the guidebook as well, and I'm happy to answer questions either here or by email afterwards. I'll point out we do have an FAQ posted on the PC7 site. Any questions that come in that are of a general nature, like can you explain this step in the proposal evaluation process, we'll take those, we'll adapt them, combine together similar questions, and put them into the FAQ for you. All right, so peer review happens. That provides information to our tech council and our governing council who make the ultimate determination about what projects to fund. All right, so now, Project Call 7 overview here. So we have a few things that are new. Minor changes to the evaluation criteria. I've already said it a couple of times, no need to dwell. We've released, as Malcolm mentioned an hour or so ago, we've released a public summary of the FHE roadmaps for the first time. The overall FHE roadmaps, we develop one portion of the roadmap per technical working group. Each of those is somewhere in the neighborhood of 15 pages long, times 11 working groups. It's well over 150, maybe 200 pages of roadmap. The public summary documents that we've produced are 1 page per technical working group, so it's still 11 pages plus some front matter for that document. And so it's quite a lot of information. The idea is to provide, especially for non-member proposers, as well as maybe non-member team members, maybe even led by a NextFlex member, to be able to share that information about the roadmaps to help make sure that there's good alignment to the priority gaps that we have within the roadmaps. And so that is one of the many purposes they serve, but in the context of a project call, that's the goal. We have that information out there. It's a simple, highly graphical document that helps with that alignment and to show what the important areas are. It also shows areas where we've made investment in the past, and so we think about trying to balance our portfolio of projects. You can think about that as well. All right, so important considerations. So it is, I've already mentioned, it's a one-stage proposal process with that pre-submission consultation sort of taking the place of a white paper round. I'm going to say it again because it's so important. We really do encourage that discussion with NextFlex through that pre-submission consultation process as part of the development of proposals. We anticipate funding 1 or more projects in every one of the topic areas. From a budgetary standpoint, we've budgeted for about 3 projects in topic 7.8, which is the open topic for new project leads. And in addition, at least 1 in every other topic. We have, given the clear focus on projects that have near-term commercial impact, we encourage teams that are industry-led. It is not a requirement that projects be industry-led, but it is an encouraged characteristic. In cases where there's not an industry lead, I would strongly encourage that you have an industry partner on a project. So if an academic institution is leading a project, that's fine. Make sure that there's an industry partner, because we really do want these projects to transition to some type of manufacturing deployment. So it may be a manufacturing process that's getting deployed into a manufacturing operation, into a factory, into a fab, as opposed to a product that's being made and put onto the market. Both are valuable, both are important and part of the mission that we have. And so putting those things into industry is important. Proposals that fall within topics, the DoD modernization priorities are viewed favorably. So we do have the mission, a dual mission, to enhance U.S. manufacturing capability and to transition technologies to DoD. So that is a characteristic that's desired. Anyone who is selected for funding, any project that's selected for funding, has to be both led by NextFlex members, and all the development partners on the project must be NextFlex members. You don't have to be a NextFlex member to submit a proposal, nor do all of your members of the team have to be NextFlex members at the time of proposal, but prior to contracting, those non-members would have to join. There's description in the guidebook that I won't try to repeat verbatim here, but that says that if you're basically buying COTS parts or if using a standard industry supply chain to produce a component or a part that you need, that's not considered development work, and that does not require NextFlex membership. So if you need to buy a PCB, board or something like that, your board house wouldn't have to be a member. If you're funding them to do development of a process to produce that board, that would require membership. And then, let's see, finally, we've selected the topics for PC7. We always welcome suggestions for future topics. If there's something that you feel falls outside of the scope of the topics that we've identified for PC7, and you'd like to discuss that with us, by all means, we can talk about whether, it does fit into this topic, or we'll take the input if you'd like to give it for future topics. All right. So, important items to consider. Building off of prior NextFlex projects or best available technologies, obviously encouraged. We're dealing with those mid-level TRL and MRL activities, so there should be plenty of activity and developments to base your proposals on. The topics are focused on addressing manufacturing gaps that are identified in the roadmaps. That means that if the project is focused on developing a manufacturing technology, it should align, but also, it's pretty clear in those cases, but if you're developing a technology demonstrator, that's differentiated from a product. We don't fund product development, but it could be a demonstrator of something that would later be developed into a product. The project should still focus on manufacturing capability development to enable those demonstrators or future products. Total funding for this project call is $5.4 million from NextFlex. Looking at historical cost share ratios that we've had in the last couple of project calls, we're estimating a total project value of $11.5 million for this project call. There's a minimum 1-to-1 cost share for every project, but historically, the average cost share has exceeded that by a substantial amount. The funding per topic ranges from $350,000 to $800,000 per topic, and you can see that in the guidebook, and we'll have that in the topic descriptions that we'll go through in just a moment here. And the durations also range by topic area from 12 to 24 months. Most of them are at an 18-month maximum. I will point out that these are maxima, both for the funding amount and the time, the duration, and so we certainly are happy to entertain proposals that ask for less money or look to perform a project faster. All right. Already talked about the cost share. You understand 50% cost share required. That's a 1-to-1 cost match. It is not required that every team member contribute equal cost share. One team member can contribute all the cost share for a project. The cost share is a contractual commitment that's made at the time of the start of the project. And so things may change within the project, but that cost share does have to stay the same. We are highly flexible. We know that this is technology and manufacturing process development work. Things don't always work out the way that we thought that they would. And so if some of the project plan needs to change, we will work with you on those sorts of things. Cost share, we need to hold. Already talked about the membership requirement and the last. All right. The whole point of what it says on this chart, which I believe is copied verbatim from the guidebook, is that NextFlex proposals are not any of the various types of government proposals. We're looking for different things. Our objectives are different. So if you're used to writing NIH proposals or NSF proposals or DARPA proposals, don't just try to reproduce what's asked for in those proposals. We try to very hard to provide information about what we're looking for in evaluating these proposals. And so making sure that you understand that, and as I've said many times already, asking us questions if there's any uncertainty is the way to go. So the idea of these projects overall is to produce information for, yes, you, the proposer. You want to advance your capability, but it's also to elevate the capability of the entire ecosystem. So the mantra that the rising tide lifts all boats really applies to these projects. The idea being every project that gets funded, the team will supply technical reports quarterly, produce a webinar quarterly that's shared to other NextFlex members so that those other members can benefit from the work that's being done. You'll share the information about how you're doing things. You'll, of course, have all the working knowledge. You will have done it, and that's quite different from being able to read a report, but everyone does get to benefit. And so when you're putting together your proposal, you want to be thinking about the fact that that is an element of the project, and it's one of the goals that we have for these projects, is that everyone should be able to benefit. So that may result in some thinking about how you decide to structure tasks within the project, or the order in which you're going to carry them out, the way you're planning on reporting, the kind of deliverables that you'd include. We ask for a lot of deliverables related to process data, materials data, designs, and things like that, and that is so that others can really understand the work that you've done and benefit from it. It's also why we don't fund product, part of the reason we don't fund product development, because no one's going to want to share the details of their product, but the development of a demonstrator that helps them to then later develop a product, that's typically pre-competitive. All right. From a timeline standpoint, I'm certainly not going to go through all of these, but I will highlight the one that's in bold, which is that the proposal submission deadline is April 14th. We ask for the cover sheet information. We have an online cover sheet submission form. We ask for that to be submitted 1 week ahead. There's a deadline of April 7th for the cover sheet submission. The purpose of that cover sheet submission is to help us to identify what proposals we're going to receive and who they're going to come from. Because when we set up our peer review process, we need to make sure that we have no conflicts of interest. So no one would be asked to review a proposal in a category where they are submitting a proposal or where they're a team member on a proposal that's being submitted. So that's how we use that information to line up our review process. It helps us to accelerate through. So that's April 7th. Anticipated rough date for a governing council review and selection of projects is June 2nd. Early June is probably the right way to think about that. We need to line up the schedules of 15 or 20 people to make that meeting happen. And this table is taken directly from the guidebook. All right. So as I think I've already said much of this, the topics are focused on developing and qualifying manufacturing processes or methods or tools. I'm not going to read this to you. That may include the development of software tools. As part of that, we ask that software tools that are developed include licenses that allow other NextFlex members to access that capability. That would follow the IP policy that we have for the Institute, which all of our members know, and non-members, we can help you understand and access that information under an NDA. But basically, the IP policy says that access is made available for internal use to NextFlex members' non-commercial internal use, and so that it would not enable commercialization of your IP. That's out of bounds, but it allows people to test it out and see if it's valuable, and then come back to you and determine whether they would want to license that. The information about processes that are developed needs to be documented and shared in such a way that others can reproduce and understand the work that's been done. Whole list of deliverable requests and requirements that are included there. And then finally, the last item that I wanted to point out is that as the field has matured, we've seen a shift from in the early days having the question from potential customers who would ask, can you do this with FHE technology? That's no longer the leading question. The questions we get now are much more about reliability and standards, and I've said this on a number of occasions in the past, but that really reflects the maturation of the field. And so enhancing the reliability of FHE technologies is a major goal that cross-cuts all of the topic areas in Project Call 7, as well as developing standards and designing and manufacturing to standards is an important element across all of the topics. It's not called out in all of the topics explicitly, but it is an element of all of them that just cross-cuts. And so thinking through how do we enhance reliability of FHE, how do we work toward developing standards, and I will say as an aside, outside of Project Call 7, any of you who are interested, all of you who are interested in working to develop standards related to FHE, let's have a conversation about that, because we are actively working on that at this time, trying to put together the groups to go and do that. We have no desire to be a standard setting organization, but we will work with standard setting organizations to develop those. All right. So we have, as you all know, we have 8 topics within Project Call 7. They align to our technical working groups, as shown on the right side of the chart here. So this is a nice summary table that identifies what the topics are at the title level, and recognize that there are lots of details below that. Maximum funding and working group alignment. All right. At this point, I'm going to hand over the mic to my colleague, Dr. Nick Morris, who's going to talk through the 8 topics for Project Call 7, and then I'll come back to talk to you about evaluation criteria.
All right, thank you, Scott. My name is Nick Morris. For those of you who don't know me, I'm the FHE Technology Manager at NextFlex. I'm going to briefly introduce the Project Call 7 topics. As Scott outlined, this is really the end of a significant development effort over the last 9 months or so through road mapping, identifying those really cross-cutting topics that would have the biggest near-term impact for the ecosystem. As Scott also pointed out, I would refer to the guidebook for additional details. This is just a brief overview of the topics on the sort of the requirement level. But the full details are within the guidebook, and you can always reach out to us if you have any specific questions. So I wanted to briefly highlight, and again, Scott touched on this, but I wanted to highlight before we talk about specific topics, that with PC6, we introduced more broadly defined topics. We really tried to open the aperture and accept solutions we weren't necessarily considering, but they directly aligned with the gaps that have been identified on the roadmaps. And that continues in Project Call 7. So really the goal is always to fill those gaps that are identified on the roadmaps. Now there is the public version for non-members to align their proposals with. But looking to those gaps that are identified in the roadmaps, we now have an idea of the relative importance of those, and we try to identify those cross-cutting opportunities, as we said. But we're always looking for that broad impact, both on the commercial and the defense applications, to really bolster FHE manufacturing domestically. Each topic does have a maximum funding and duration, but again, we do seek lower funding levels. It's always welcome if you come in under the maximum funding and time duration. But what I really want to highlight is that there's a set of, in each topic description, which I'll go over, there's a set of requirements, and then there's a list of example topics. And we're careful to list those as examples. We don't want to list those as subtopics, because you do not need to directly apply to one of the subtopics there, either all of it or part of it, as long as it aligns to solving one of the gaps on the roadmap. That's really what we're looking for. So a proposal may address only part of one of the example areas. It doesn't have to address one of the example areas at all. You don't get bonus points for addressing one of those, as long as it still identifies what roadmap gap or what gap that you identify in the area that you're trying to solve, and justification of why that gap's important to the ecosystem. So first, topic 7.1, advanced packaging approaches for IC integration and FHE devices. This really aligns with what Malcolm mentioned just at the earlier talk, where we're really trying to take the lead in a lot of these advanced packaging applications, where we think FHE and FHE manufacturing and additive solutions can really afford a lot of opportunities in semiconductor advanced packaging. So this is a $450,000 maximum institute fund, up to 18-month duration, and it really addresses those capabilities of complexity of IC integration on either flex substrates or using FHE and additive manufacturing techniques, as we encompass under the FHE umbrella. So looking at packaging approaches like heterogeneous integration, 3D package on package, chip in package, active interposers, high density interconnects, looking at 2D, 2.5D, 3D integration of chips using these techniques. So these are the requirements. As I said, all of the topics follow this, have a list of topic requirements, that's the paragraph there, and then a list of subtopic or examples that your proposal can align to, but is not required to. And in this case, looking at high density flex interconnects, so looking at the manufacturability of flex interconnects with pitches on the order of 50 microns, looking at highly precise die alignment for integration, for IC integration, things along those lines. There's a detailed description. And those examples are really meant to give you an idea of technical areas of interest. Again, they're not exclusive to those, but also the scope of a project that we would expect for this amount of funding in this duration. The other is looking at more broadly heterogeneous integration. So looking at using FHE manufacturing approaches to integrate several functionalities onto a single chip platform, and either on a flexible substrate or using FHE manufacturing and additive approaches. And that's looking at integrating things like power management, processing, electronic sensing, computation, RF communications, even microfluidics onto a single chip platform and showing the reliability and performance of these advanced packages. Topic 7.2, this is additively manufactured electronic components and devices. And this is really addressing a need for more traditional PCB manufacturing to integrate either fully additive or semi-additive approaches into things like passives and embedded passives into PCB manufacturing. So there's a big opportunity there, but there needs to be significant technology development and more specifically, as Scott mentioned, proof of reliability and leading to alignment with existing standards or augmentation of existing standards or development of new standards for FHE approaches. Again, we're not going to develop those standards, but we need to do a lot of data generation and proving out of reliability of these technologies to get to that point where we can get adoption of these processes into PCB manufacturing. So this topic seeks to address the gap that currently exists in that area and address and advance the development and integration of additive tools for electronic components and PCB manufacturing. So some examples of potential topics include reliability testing and standardization of additively manufactured circuits. So looking at more recent approaches to fully additive electronics and verifying their reliability and moving towards standards, as I mentioned, from something like IPC or MIL standards, and verifying and doing a comparative analysis between traditional methods and FHE methods for fully additively manufactured electronics. Another is manufacturing of embedded printed passive components, so making printing of multi-layer electronics, both conductive and dielectric elements, but focus on embedding printed passive components, so resistors, capacitors, inductors that have proven reliability and repeatability in an embedded multi-layer printed structure. And finally, digital manufacturing of reliable and multi-layer FHE electronics. So looking at digital tools like inkjet and aerosol jet that can do multi-material printing, again, printing multi-layers of conductors and dielectrics, but also looking at surface mount component attach and IC integration, but all on a digital platform. So you can rapidly go from prototyping with minimum engineering efforts to go from prototyping to a low volume manufacturing. So different opportunities there, but looking at those digital manufacturing tool development. Topic 7.3 is improved environmental sustainability of electronics with FHE manufacturing. And this is a topic that's come out of a lot of interest from our members in discussions we've had over the last year of growing interest and more information on how FHE and FHE approaches can lead to more sustainable electronics manufacturing. And this is a big opportunity space that we see, but hasn't been a lot of that foundational work that can really show the potential of FHE for improved sustainability, environmental sustainability in a lot of different areas. That encompasses things like recyclability, disposal of parts, looking at the full product life cycle, trying to account for the environmental impact of devices, especially if you're doing something like a disposable sensor or a disposable electronic device. E-waste generation is a big concern. So trying to account for that from the design phase and showing the impact throughout the entire life cycle is very important. So this topic seeks to look at the state of the art and trying to establish how FHE can really be a solution to a number of these opportunities within the environmental sustainability area. And I will point out on Thursday in our technical council meeting, we do have a session about FHE and electronics manufacturing for sustainability for members. So examples in that area include full product lifecycle modeling of FHE and printed electronics, as I mentioned, trying to account for all of that, doing a comparative analysis of traditional electronics and the eco impact of the life cycle of traditional versus ones that would be manufactured with an FHE approach. Repairing of printed FHE devices for reduced e-waste generation. This goes to sustainment of electronics, but also has an impact with sustainability, environmental sustainability. Looking at if you have a printed trace and it needs repaired, how can you repair it for a reliable repair? But that is, in fact, reducing the eventual e-waste if you can repair parts as opposed to continually disposing of parts that have some sort of failure. And physical integration of flexible batteries for improved electronics recycling. So one of the most difficult components of a device to recycle is the battery. So looking at creative ways of connecting and integrating batteries into a demonstrator that can really show how it can improve recyclability and reclamation of materials during recycling. Topic 7.4, which is looking at manufacturing of soft and stretchable electronics. This is another $450,000 maximum institute-funded effort, up to 18 months duration. And this is really looking at soft electronics that have a lot of potential for applications and things like wearable devices that integrate with the human body, looking at soft robotics, textile integrated if you're looking to laminate soft the TPU-type electronics into textiles and garments. There's a lot of challenges there that still need to be addressed. And this topic seeks development and evaluation of those manufacturing techniques for soft and stretchable electronics. So some potential applications include examples include FHE interfaces for rigid flex and stretch components. So one of the biggest challenges is electromechanical coupling of those stretch components with a rigid or flexible body. So there's ad hoc solutions and strain isolation that takes place, but we're really looking towards what is a manufacturable solution to connecting highly stretchable components with flex and rigid components. So that's an ongoing issue that we're looking for solutions for. 3D printing of active soft materials with embedded FHEs. So looking at printing of something like a soft elastomeric composite that has additional functionalities like actuation or sensing, and be able to print that, printing of hyper-elastic soft materials, but still at high resolution can be difficult. So that's an area that a number of the working groups have identified, including soft robotics and the materials working group of solutions there, especially materials that have low hysteresis and are highly stretchable. Another example, manufacturing soft embedded microchannels for FHE devices. So looking at things, how to manufacture microchannels that have, for microfluidics, for a wearable device that does biofluid handling and monitoring, or again, soft robotics that have pneumatic or hydraulic actuation through microchannels, how to fabricate those reliably and integrate those with FHE devices and technologies. Topic 7.5, enhanced dielectric materials and manufacturing methods for FHE devices. Another $450,000 maximum and an 18-month duration. And this is really looking at those dielectrics of substrates, dielectrics, encapsulants, overmolds, and pushing the performance and the use cases of those dielectrics, whether it be for RF applications or encapsulation and overmolding applications. So there's a number of gaps. I would say doing an assessment over the last year of our funding portfolio of project calls that we've funded, over 6 project calls now. and looking at the gaps that are identified in the materials roadmap as well as the integrated antenna array roadmap. There's been a somewhat lack of focus on dielectric development over the last several cycles, and we're looking to push some development work in that area. One such example is printable dielectric materials for RF packaging, specifically talking about low loss materials, low dielectric constant materials, with the caveat that low temperature processing is key. Printable, so looking at aerosol jet printed dielectrics that have low loss capabilities, but are UV cured or photo centered. So keeping the processing conditions under about 160 degrees C for specific flexible applications. Another potential example is encapsulation of thin dies on flex substrates. So encapsulating integrated thin dies on flexible or stretchable substrates for high moisture, for harsh environments with proven reliability testing is just one example there. But really looking at how do we reliably either encapsulate thin dies directly, looking at overmolding processes, but how do we reliably protect those thin dies that are integrated on flex and stretch and subjected to high stresses and strains. Topic 7.6, manufacturing of FHE-enabled automotive components, another $450,000 maximum budget and 18-month duration. This is an exciting topic that we're looking at that comes out of the newest technical working group that we launched at the end of last year, looking at automotive applications for FHE electronics. And automotive is really a exciting application space that is demanding more and more FHE technologies, but there's a big hurdle in proving the reliability for automotive applications, and that's a high bar, and trying to integrate with automotive tiered suppliers and proving out that reliability and sustained reliability of these devices, that needs to be, there's a lot of work there that needs to be proven out, but there's a ton of potential application spaces given EVs, autonomous vehicles. Automobiles are really becoming a integrated network of sensors, and being able to connect those and seamlessly integrate those into the exteriors and interiors of automobiles or cockpits or similar is really an opportunity space for FHE technologies. And this project looks to show the potential there, demonstrate and evaluate which FHE manufacturing technologies that are relevant to automotive and really show their potential in a number of different potential areas. So the first draft of the automotive roadmap is published on the member portal, as well as the summary within the FHE manufacturing roadmap summaries for non-members. Some potential examples include evaluation of in-mold electronics manufacturing processes and reliability. So one of the big applications in automotive is integrating electronics such as touch or lighting into interior body panels or interior panels, exterior body panels. A lot of that's done through thermoforming of plastics with printed traces and integrated components, and there's a lot of stresses that happen there. So looking specifically at how either pre or post forming, looking at the reliability of those thermoformed electronics. Film on structure FHE integration for automotive applications. Again, another application space where laminates play a big role in integrating electronics into potential automotive surfaces. Looking at integrating those processes into existing or easily integrated into current automotive manufacturing techniques is for near-term wins is really the focus there. And finally, connectors for printed electronic circuits for module-to-module interconnection. This is really looking at being able to print conformally, typically connecting those sensor arrays or those electronic arrays on complex geometries, trying to replace wiring harnesses with copper wire and greatly reducing the weight for automobiles for increased range or fuel economy. But being able to replace those with some sort of printed conformal trace is really the goal of that example. Topic 7.7, wearable human monitoring interface demonstrator. This one has a ceiling of $800,000 and up to a 24-month duration. And this topic seeks demonstration and evaluation of human monitoring systems. So really integrating FHE with the human body for different applications. It could be human monitoring systems, but there are other potential avenues to take this. But looking at the manufacturing approaches and system integration tools that can transfer to volume manufacturing of things like biopotential electrodes, wearables, integration of human to machines for exoskeletons or prostheses. This is really a broad area that we want to increase focus of integrating electronics with the human body or biological body. And this is, I think the recent pandemic has really emphasized a lot of wearable medical tracking opportunities. We want to have a nice demonstrator here that shows the potential of that next generation of human monitoring or integration of electronics with the human form. So potential application or potential examples include biopotential electrodes with improved signal quality for dynamic environments, looking at things like EEG, EMG integration. It's really a packaging challenge, integrating them into having good signal quality for a wearer, but with the requirements that that environment might be very dynamic, whether it be in a defense application or a athletic or fitness application, but continuing to get reliable, high quality data that's comparable to a rigid standard. Low cost, single use vital sign monitoring devices. So this is looking at greatly reducing the cost and increasing the manufacturing volume of something that can monitor vital signs such as blood pressure, temperature, blood oxygen levels. But really focusing on the manufacturing techniques that can make a integrated device at low cost and high volume. And finally, textile integrated electronics with wearables for operator comfort and human robot interfacing. As I mentioned, a potential option or potential avenue here is looking at using electronics and potential microfluidics at that integration between human and machine to either for comfort, so you can do pressure regulation, active pressure regulation between the wearer and the machine, or heated or cooled, actively heated or cooled garments for extreme environments. Looking at integrating functionality more, next level of functionality into textile integrated electronics, but really focusing on that, doing that reliably, because there's a lot of challenges there as well. And finally, topic 7.8, this is our open topic for new project leads. This is, we first kicked this off in project call 6 and had a lot of success identifying projects that are open. They must identify which roadmap gaps that they are addressing and which technical working group or working groups they align with. But really the goal here is to increase the diversity of new project leads, and we're very successful at that in PC6. We continue, we're going to continue that in PC7 and onward, because we always want to continue to build the entire ecosystem, and it's very important, and it aligns well with the NextFlex mission to do just that. So, as I said, the projects must align with the technical working group roadmaps. You must call out in your proposal which gaps that you're solving. And again, this plays into the importance of those pre-submission consultations, because we can help point you in the direction on the roadmaps of technical gaps of interest for members and non-members. But aligning to those needs is very important. But the key caveat here, which this is the only topic that has an eligibility requirement like this, and it's that the lead organizer, the lead proposer, the organization must not have led a project call project in either of the last 2 project calls, so project call 5 or project call 6. We do still strongly encourage teaming, so developers can have led a project in 5 or 6, but the lead organization cannot have been a lead organization in project call 5 or 6. So as Scott mentioned, we do anticipate to fund multiple awards. The ceiling for this is slightly lower at $350,000 of maximum government funds and a 12-month duration, but we do anticipate at this point likely around 3 proposals in this area to be funded, depending on the quality and the number of proposals received. So with that, I'll hand it back over to Scott to talk about the evaluation criteria.
All right, thank you, Nick. All right, so we're getting toward the end of the presentation here, and so I strongly encourage any of you in the room who have questions to start thinking about those, and we'll give a chance to ask them. If you're joining us remotely, you can use the Q&A that's on the Whova site to enter your questions, and we'll address those in just a few moments. All right, so as I mentioned earlier, we've made some subtle changes to the proposal evaluation process, mostly to the description of that process for Project Call 7 to reflect the way that we go about this evaluation and ranking of proposals. So we start with a peer review process. So the proposals are all distributed to a slate of reviewers that primarily which is primarily made up of NextFlex members and government subject matter experts and NextFlex staff. On a few occasions in the past, we have used third-party individuals who are subject matter experts on something that we felt the need to go out and have an evaluation of. And in that case, we have those people under NDA. It's described in the guidebook, so the information doesn't get out there about your proposals, in any way that would be concerning. The reviewers evaluate the proposals against a number of criteria that are described in the guidebook, and we actually have included a copy of the score sheet that we send to the reviewers as I think it's Appendix D in the guidebook, so you can see exactly how we request that information. That's the numerical scoring, and then there's also some free-form commenting that we allow them to do, we ask them to do. So they provide those scores and in the different categories as well as comments. Nick and I will analyze and analyze and compile all of the reviews and summarize the comments for the NextFlex Technical Council. The Tech Council, we will also meet with the reviewers in cases where there might be any questions. The Tech Council receives that summarized information from the reviewers and votes a set of recommendations. Those recommendations go to the NextFlex Governing Council, which votes to select the projects for award negotiation. All right, so I'm not going to read through this, and I realize that for anyone in the room, this is too small to read. The point that I want to make here is that we have 13 review criteria that are in I guess it's technically the fourth column here under criteria. Those are the criteria that we ask the reviewers to rank each proposal in. The subtle change we've made to the review process here is that we have identified explicitly that the first 7 of those are the technical criteria, and we actually reordered them so that they would be consecutive on this list. And then we have a set of 6 non-technical criteria. And rather than producing a single score by averaging all of those criteria, we're producing an average for the technical score and an average for the non-technical score. That reflects the fact that generally it is those proposals which have the highest technical scoring that end up being selected. This is not a purely numerically driven process. If a proposal is ahead by 0.0001, that doesn't mean it's going to get selected over that other one. That difference is not statistically significant. We've done the analysis. We understand these things. We also look at the comments that come back from the reviewers, and we have to balance a portfolio of projects. And so those are all of those elements are included in the proposal in the project selection process. And so, however, as I said, we're looking at the technical score. That will generally create a ranking for us of proposals, and we use the non-technical criteria, to identify potential outliers, either low or high, as well as to get a sense of where the proposals stand relative to each other and make sure that they meet the standard that we have for projects. We also look very strongly at the reviewer comments, and that non-technical scoring can help us to understand what those reviewer comments mean. Nick and I review all of the proposals as well, so we understand what the content of them is. And in every project call in the past, we've had at least some categories in which we've gotten together reviewers to have a discussion to understand better. That we do that in cases where proposals are ranked very close to each other, as well as in cases where the ranking might have come out quite different than we might have expected from our own reviews. All right, so the evaluation and selection criteria, I've already said, we produce these 2 scores. We then average across all of the reviewers and we provide that information to the Tech Council. We also summarize all of the comments. To give an idea for people who have not been involved in the peer review process before, a typical NextFlex proposal goes out to somewhere in the neighborhood of 12 reviewers. We try to have the same reviewers review all proposals in a topic area. In cases where we have too many proposals in a topic area, to realistically give to a single reviewer, which we kind of cap around 5 or 6 proposals per reviewer, then we split it up and we diversify. We make sure that there are overlapping reviewers for any proposal. So we end up with project call 6. We actually added it up. I think we had nearly 600 individual proposal reviews, and we had more than 100 reviewers doing those reviews. So these go out. They have a lot of people looking at each individual proposal, so it's certainly not a single reviewer who has any outweighted say in how the proposals are evaluated. So the scores and the comments, as I mentioned, we compile them and we use them very strongly in the Tech Council discussion and voting. And then the Governing Council is going to make the final determination based on those criteria that I've already mentioned. The scoring, the reviewer comments, and a balance of project portfolio are the main things that they would consider. All right, so that is the end of our presentation session here. And before we go into the teaming event, we'll stop and take questions. So Nick and I are happy to answer any questions from our live audience as well as from online. All right, Joey, I see your hand first. Yep. We're going to bring a mic around, I think. Yeah, Laura's bringing a mic to you. And that's so that our online audience hopefully will be able to hear you. And if they can't, I'll just repeat back. Hold it close.
Hold it close. So I have two questions. One, can a non-member go into the open project call, assuming they would become members?
Into the topic 7.8, the open topic
Yes.
for new leads? Absolutely, yep.
And
The only criteria there is that the lead proposer must not have led a project in PC 5 or 6. And then there's also a criteria about the percentage of funding that has to go to that lead. So it can't be gamed so that technically they're the lead, but they're doing 5% of the work or something.
But the lead could be a non-member at this juncture.
The lead can be a non-member, yep.
And then the second question is very specific. When you talked about the automotive, are you looking for injection molding, thermoforming specifically, or dependent on what exactly is the piece?
I believe I think that's in one of the examples.
Okay.
And so, and Nick had said this, but we've structured the topics so that we have the topic definition, and those are kind of the requirements. You have to meet the criteria that are in the topic area. And then we have examples that are intended for a few purposes. The examples identify areas that are of known interest, that are known to align to the guidebook. And truthfully, we include examples in areas where we would be very interested in seeing proposals, but they are not restrictive. So if you've got something else that aligns to the topic area, so you can choose a part of what's in one of those topics for those examples, perhaps, or something that's not in any of the examples but still aligns to the topic, that would be that proposal would be considered equally. And proposing something that matches up perfectly to the example doesn't give. I think he and I have used these words back and forth with each other. You don't get bonus points for that. So if injection molding of the part or thermoforming or whatever process makes sense for manufacturing the component, that automotive component that would be of interest for that proposal, that's perfectly fine. If there's another process, that's okay too.
Okay, great, thanks.
Yep. Got a couple more questions in the room. While the mic is heading over there, I've got a couple of questions that have come from online. So what is the timeline for pre-submission consultation? I believe we've got the date listed in the guidebook. You can start contacting us anytime you want. I believe we've said that we'll start having those pre-submission consultations next week.
Are there no agency-funded sections this time?
There are no agency-funded topics. No, that's right. There are no agency-funded topics within this project call. We do have agency-funded projects that come in, whenever an agency identifies a particular project and it gets added to the cooperative agreement. So I think it's reasonable to think that there would be, that there may be, or I should say may be, agency-funded topics that come about throughout the course of the year, but they're not included as part of PC7.
Yeah, I got a question about the schedule. You didn't have an award date for planning. Is there a specific date that the project calls would be awarded on?
Sure. So the date that we have in there is a target, really, of June 2nd, or let's say early June, for the Governing Council to make its determination. We would notify the selected teams within a week of that date. It just takes us some time to put together the information and communicate it out. I think with PC6, we sent those notifications about 2 days after the Governing Council meeting, but we allow ourselves a week because calendars do those things to us sometimes. Our goal is to, within days of notification, to provide the development agreement template and begin having the selected teams putting together their statements of work and reviewing the terms and conditions. I think the first project was, I think the first development agreement was signed about 4 weeks after notification last year. And so, our goal is to get all the projects on contract as quickly as possible. So it really comes down to the timeline for negotiating terms and conditions, which are pretty standard, and yet somehow, even with very minor changes, it can take quite a while. So I would, If I were doing it, I would estimate something like, I don't know, 45 or 60 days after the notification as being a reasonable time to plan for, as long as you're willing to, work to get your lawyers to review and work through agreements quickly. More questions in the room, and I'm going to take one from online. For topic 7.3, does environmental benefit include both material, safe, reuse, recycle, as well as significant energy savings within the manufacturing process? Simple answer is yes. We're looking at total environmental benefit of environmental sustainability of the processes and the devices that are being manufactured. There's a reference in one of the examples to life cycle assessment, and that's exactly why, because we're looking at the total benefit, and life cycle assessment does exactly that. It looks at what's the total environmental impact of your processes and your material selection and your potential for recycle and everything that goes into it, energy use in your manufacturing process, waste streams in your manufacturing process, everything. And so potential proposal could focus on some part of that, all of that. It would all be of interest to us. I will say that within the discussions we've had about environmental sustainability of FHE, the energy use is one of the things that we think a lot about, because when you do additive processing, the thermal history and the waste streams are considerably different than if you're doing standard subtractive processing of printed circuit boards. So there's a potentially high benefit of using those additive processes for electronics manufacturing overall. But it's all in scope. Just stick to whatever's in the topic description, and you're good. And I'm happy to answer specific questions as part of that pre-consultation or pre-submission consultation process. Should take another question from online. Do we have another one in the room? I'll do online while we wait for hands. Are reviewers' scores weighted against the reviewer's average before scores are totaled? Okay, now we're down in the really nitty-gritty of the evaluation process. We have looked at it and tried to determine whether we can adjust for reviewer to reviewer variability in the past, and it does not look like our sample sizes are great enough to be able to do that in a way that actually changes the overall outcome. So no, we actually average exactly as the reviewers score them. We do have a rubric that we provide to reviewers as part of the scorecard that identifies, a 1 is meant to refer to this, a 2, it's a 1 through 5 scoring. We identify what a 1 means, a 3 means, and a 5 means. They can interpolate between those for 2 and 4 on their own. That's the way that we have tried to bring reviewers into better alignment with each other. But statistically, we haven't seen that trying to account for reviewer average really has any meaning. One reviewer may think that the proposals may actually believe that the proposals are of a different quality, and so that it's hard to know whether that is an intentional bias or a difference in how they think about the numbering systems. Any other questions in the room or online? We do have about a 20-second delay for the online audience, so we'll give them a little while. They may have thought of an additional question based on the previous answer. Oh, I've got a question over here, Laura.
I was curious about the budget numbers listed in the project call. So those are the maximum amount of funds for an individual project under each topic. You expect to fund multiple projects under each topic, or how does it work?
So the budget numbers that are listed are the maximum per project. So a proposal can come in requesting up to that amount in funding. So total project value is that plus cost share. We anticipate funding. Well, we've identified the $5.4 million overall for the project call. Doing the math, and with my comment that we anticipate 3 in topic 7.8, that would give you an extra 2 projects, assuming that they're at the $450,000 level, which is what most of the other topics are. So we anticipate 1 or more in each of the topic areas. We have not predetermined which topics would be likely to get a second or third project to be funded. That's going to depend on the proposals that come in, quality, distribution, and whatnot. Okay. If we don't have any more questions, then we will next move on to the teaming event. And so I don't know the final count. We were still receiving some slides this morning, but 20-some is, I believe, the number of slides that we've received from potential proposers or team members to share information about their capabilities. And so we did a teaming event for PC6, for those of you who were not part of that. We did a teaming event for PC6, highly successful, in which we used this format exactly. Potential proposers or team members could submit a single slide. They'd get a minute to present. And the point of this is to identify what your interests are, what your capabilities are, and what you might be looking for in team members. Maybe you're looking to join somebody else's team. Maybe you're looking to have somebody join your team. You're looking to fill a specific gap within your project, your proposal team. It's really up to the proposer to identify what it is that they're looking for and how they want to share information. And so what you'll see in the next, I don't know, half hour, 45 minutes is going to be highly variable from one to another, just reflecting the different capabilities, interests, needs, and objectives for these presentations. And so we're going to go, the way we're going to do this is we're going to go by topic. I should say there may be some presenters, there are some presenters who will present more than once per topic. If they're interested in a proposal in 7.1 and 7.5, they would have two. They may have some with more than two. So we'll go topic by topic. We'll start with 7.1. First, we'll take the in-person presenters, and then we'll switch to the online presenters. And then we'll move on to 7.2 and do the same, in-person followed by online, trying to just keep things moving. The slides will be brought up by our colleagues across the room. And so when it's your turn, just ask you for the in-person folks just to come up. For those of you who are online presenting, those folks are joined by a Zoom meeting so that they can use the audio stream from that to present. So I think I've just gone through this without saying anything, or without seeing the slide. So we're not taking Q&A. I should have added, we're not taking Q&A on these. That is intended that you'll connect afterwards. You can connect through the Whova app, if either in the room or online, or we can provide the contact information. Everybody's contact information should also be available in Whova that you use to register for the symposium. So, all right. Topic 7.1 is our advanced packaging approaches for IC integration and FHE device topic. And why don't we go to the first presenter? And then I'm going to step aside and let other people take over. All right, Pradeep, you are up.
Good morning. My name is Pradeep Lal. I'm a professor at Auburn University. So we are going to lead a team on additively fabricated heterogeneous packaging solution. This is in topic 7.1. We envision that the program is going to focus on packaging approaches that enable 2.5D, so basically building planar to create the third dimension, or 3D integration of ICs in a flexible form factor device. And specifically, the focus will be on power management, signal processing, and electronic sensing with onboard computation. And we hope to be able to create a product demonstrator for this. Some of the background in terms of work that has been performed by the team at Auburn. So we have a significant body of work in component attachment on additively printed circuits, on aerosol jet, inkjet, and direct write and stencil printed circuits in PC6.4 that the team is currently undertaking on planar architectures that we hope to be able to leverage. We have also worked on flexible encapsulation of FHE devices in PC 4.1, where we identified a number of flexible packaging solutions for assembly and integration of devices that we hope to be able to leverage as well. Z-axis interconnects that would be required for heterogeneous packaging integrations, some things that we developed in OPC 1.0, and as Scott mentioned, reliability is a cross-cutting attribute, so we hope to be able to use some of the test and reliability platforms that were developed in PC 2.5 and also in PC 4.5. So the capabilities that we seek, we are looking for newer materials beyond what we have previously used for flexible encapsulation. So companies that have offerings in this particular space that would like to engage with us, we'd love to hear from you. Solder companies, there are a lot of materials that are out there currently. Some of them are mainstream materials that are commonly known, but there are some unique materials that can be processed at low temperatures. We'd like to be able to engage with companies that have product offerings. ACA and isotropic conductive adhesives that would allow for component integration. We'd love to be able to connect with companies. And of course, the intent is to be able to create these in volume. So third-party contract manufacturers that would like to leverage their current processes or process lines to be able to look at process viability as a part of the program, we'd love to be able to hear from you as well. Thank you.
Thanks, Pradeep. All right, our next presenter.
Sounds like the two next ones we don't have on here yet, so can I skip ahead?
Yep, let's skip ahead.
Okay.
Okay, so I guess we had only one in person, is that right?
Correct.
Okay, so we will come back. We will come back.
Okay. We don't have any
Okay, so for topic 7.2 is our additively manufactured electronic components and devices topic, and we will start with the in-house presenters. All right. Ahmed, yes. And I will say, in the interest of time, I'm not going to introduce our presenters, but I'll allow them to introduce themselves.
Hi, good morning. Good to see you again. So this is about additively manufactured electronic components. We have a project on PC6 that you can see some of the results posted of printing passive components, capacitors and resistors. We're looking at 7.2, and we want to add to this the capability to print active components, such as transistors, diodes, and so forth. And so this is all additive, all room temperature, the capacitors here. The dielectric intercapacitors can be done with UV curing, or can be done with high temperature curing. The capacitors are basically, could be silicon dioxide, could be hafnium dioxide, could be a variety of dielectrics. And we see that the electric constant is pretty close to the theoretical value after printing. No pinholes or anything like that. And so with the proposal here, we want to go beyond the passive components and go to the active components. So that includes using silicon and using single crystal silicon for printing those devices. So this is as you can see, we've been developing this technology for a long time. Actually, Joey was part of that a long time ago. So so this is basically a very high throughput. You print one layer per minute, whether you're doing nano or micro scale, for example. And we're leveraging this technology to do not the full chip yet, but to do basically components to help with the packaging. So when you print a trace, you print your components at the same time. And that means that the interposer or the board size will shrink by a factor of 10 or 20. And also the number of components will shrink, of course, because you can go from a circuit board or an interposer that would have 30 components or 40 components down to about 2 or 3, which are basically the chips that you're integrating. So basically we're looking for, of course, we're looking for partners from industry to work with on this project, because we're manufacturing people mainly. We look for people to help us with the design, to help us with the testing, and the concept and the application as well. Thank you.
Thanks, Ahmed. I believe we have a couple more in person. So Pete, all right. So we have Pete Hugger from General Dynamics.
Hey, I'm Pete Huger from General Dynamics. At our location, we have been a long time manufacturer of a lot of the airborne radomes we all know and love. Some of them are shown here. We've been doing some work in PC6 to try to bring more additive technology in a hybrid way into radome manufacture. So in aerospace, we really love prepregs. We really love laminates for their mechanical strength. So hybridizing, for example, FSS type elements like you see in the blue box here, together with that laminate manufacture, which has also been demonstrated to some degree with antennas previously. Moving forward to PC7, we would like to bring active components into this hybridized manufacturing. So here in the slide, you can see some notional implementations of how that might work, moving to more complex geometries, doubly curved surfaces, applying an antenna with the antenna front-end components onto that surface, balance, amplifiers, things of that nature, then encapsulating that in some fashion, and then applying more pre-preg, and then here is a notional functionalization structure that's on top of that, the crosses that you see here. So we would like to bring this together into a product that could be performance tested, perhaps evaluated for its mechanical and other types of resilience. So as a radome manufacturer, what we bring to that is test capability, RF test capability. We apply tooling to these types of problems. As you can see, capability salt, a rapid tooling manufacturer would be an attractive addition to this. We need partners, and then our capabilities, of course, would be the laminate layup, the cures, all that kind of stuff, including some RF design components. And then we want partners who have additional far field test capabilities, the conformal print aspect, rapid tooling manufacturer, and as I might imagine, if you have an active vision FDM type printer for a compatibility layer, so when we're laying up those laminates on top of active components, we can fill that space efficiently. That would be an attractive thing. And then, of course, antenna design. Thanks.
Thank you, Pete. I think we have one more in person. Pradeep, you're up. And then we're going to go over to our online presenters.
Thank you, Scott. Again, my name is Pradeep Lal from Auburn University. The focus of the program that we are trying to form a team on is on manufacturing rules and test levels for yield, reliability, and performance of embedded printed passives. So the focus is on print processes to be able to assure a high yield in an actual high volume line, to be able to assure performance is comparable to regular pick and place components, and reliability is at par, if not better, than existing component form factors. And to be able to create a fully integrated additively manufactured solution that does that. So what we'd be leveraging in this particular program is a significant body of work on closed loop control of printed passives that is being conducted right now in PC6.5 jointly with Boeing at the present time, where we are using optical and hyperspectral methods to be able to create a closed loop control process. We also want to be able to leverage interconnection of these printed passives through the various layers in a flexible encapsulation solution using Z-axis interconnects. And again, we'll leverage some of our prior work in OPC 1.0, which focused on that specific aspect of process development. And more importantly, we'll like to quantify the defect propensity through quantification of sigma levels as a part of these manufacturing rules and test level development. So specific capabilities that we seek, again, we have a baseline set of materials identified, but what we are really looking for are ink companies with offerings in dielectrics that could fit into this particular space. High conductivity, low sintering temperature inks that could fit into this particular space. Again, we have some offerings that are there, but we want to be more inclusive and flexible encapsulation companies. Thank you.
And I misspoke. We have one more in-person presenter, Dr. Shen Ren from University of Buffalo.
Thanks, John. Good morning, everyone. Finally meeting in person today. So actually, I bring two samples here. One is our nanostructured copper, and the other one is our molecular ink copper. So anyone's interested, please come to me and we can share the details on this. So on this slide, I hope everybody can read and what's the status of current ink. I mean, including copper, silver. And our copper, I would say, there's a how to distinguish our copper from all the other people are doing on copper and the silver. There are 4 distinguished characteristics. First, oxidation and corrosion resistant for a very broad temperature range. So for our current point, PC 6.8, we are targeting for 1,000 degrees C, actually application for copper ink. And the other, it's a scalability and low cost, high performance. Our best ink can go up to 50% of IACS in terms of the connectivity. And third characteristic is printable and stability. We can put the ink without any cold storage and shipping. Shelf lifetime can be over 1 year. And ink itself is very stable as well. And the last characteristic is a high current density and opacities. So if you pass the high current, and that's how our copper ink make a difference. And that's basically 4 different characteristics of our copper ink. And if anybody's interested, and we can chat offline. So, and we are also looking to the partners. And by the way, with the support from NextFlex and the Army Research Lab, we are able to now commercialize our copper ink. And the company actually just got launched a Copperium. And if anyone's interested, please check out our website. And I'm not trying here to sell any ink to everyone, but if you're interested, we can talk and collaborate. And for application-wise, we are interested to develop the applications by using the copper ink. All right, thank you, everyone. And I'll also bring some of the demonstration unit of printed copper and a few quick slides.
All right. Thanks, Shen. Now we're going to go to our, I guess, our first online presenter.
So good morning. I'm Alka Meikertlu from UMass Lowell. And I just kind of put on examples of the current capabilities we have and what we've been working on, both from support of NextFlex as well as other agencies. One thing that I'd like to say is one of our strengths, aside from having an array of various printers that can do aerosol jet, direct print, and 5-axis for conformal printing, we do a lot of in-house ink development. And so, for example, what you see on the lower right, we have a patented ink that is the AGBST. It's a resistive ink. It comes down as an insulator. And then when it is either heated thermally or actually you can laser sinter it to get various resistors. And we have different designs that we've been able to make with this when we actually use this ink as a mask. And moreover, we have developed another UV ink that allows us to stabilize this. Going back to, let me go in order, the first top left picture. This is a purely additively manufactured interconnect. It's basically an interposer that is printed with the end script, and then we plannerize it with our, again, in-house patented UV curable dielectrics. And then we have another material that we have, which is a gasket, and then we print over both the gasket onto the board for testing. What you see on the top middle is a printed resistor. This has very, very good, small resolution, and this we've used in various technology protection programs. We have recently been working on implementing our various capabilities onto e-textiles. So here you have some meta surfaces that are used for anti-jamming applications. On the bottom left, we have our, we've been doing a lot of work on bare die integration and working on very thin die. We've had some projects with Raytheon and AFRL on this. And we have developed another UV ink where we can use it as not only a ramp material, but also for printing on top of these transmission lines, like let's say a capacitor. And I didn't include that, but we can also print capacitors. We have some really high DK dielectric ink based on BST or barium strontium titanate, which can also be tuned. And so I don't know if I'm over my time limit, but some of the presenters that presented for this, I think we have a lot of synergistic ideas. I think General Dynamics mentioned conformal printing, antenna design, antenna characterization. We've got that. Auburn mentioned some things about novel inks. So if anyone's interested, you can contact me, and someone wrote my name and information there. So looking forward to collaborations. Thank you.
Thanks, Akim. All right. Our next presenter should be Madhu Stemmerman from Sunray Scientific.
Good morning. I'm Madhu Stemmerman with Sunray Scientific. We are a material solution provider. We offer a electrical interconnect material, which is called Z-Tech. It is a Z-axis anisotropic conductive epoxy, which is magnetically aligned. And we also offer a flexible encapsulant. The beauty of our technology is we have exceptional adhesion to both flexible and rigid substrates. We have the ability to cure at 70 degrees C and greater. We also don't require any pressure, and we have the ability to get down to fine pitch, about 100 micron pad pitch for high density interconnections. We've actually partnered with a variety of companies and universities to include Molex, UMass Lowell, Auburn University, Boeing, Lockheed, Raytheon, a variety of companies. And basically what our goal is to demonstrate robustness, reliability, and scalability of our technology. So we're working across a variety of applications. We're looking to partner with universities as well as companies in order to work on your applications and again, demonstrate that robustness, the reliability, and scalability. I can be reached. You can see my email address below, and look forward to speaking with you and collaborating.
All right, thank you, Madhu. All right, next we're going to move to topic 7.3, the improved environmental sustainability of electronics with FHE manufacturing. Our first presenter is in person, Jeff Yen with Etherdyne. There you go.
Hi everyone, sorry about the font and the light. So this is a very simple slide. So we are Etherdyne technology. We do wireless power. So we are enabling sensors, actuator to be wire-free and battery-free. I think one of the goal is to have the new technology that can do stickytronics, so sticker electronics. So our system is very simple, two parts. One is a transmitting part. We're using a magnetic resonance at a 7 megahertz range. So this is not a high frequency, this is low frequency. The antenna is a loop antenna, not the tiny small printed antenna, which is we deliver power up to watt to 10 watt level. So it is power electronics, and for this proposed project, we are focusing on the receiving end, which is a sensor end and actuator end. And then we are looking for people with expertise in the printed electronics and the flexible electronics that can actually, we can actually collaborate, and we can hopefully to remove the batteries in this ecosystem. Thank you.
Thank you, Jeff. All right. Our second presenter, Pradeep Lal. And then we're going to move to the virtual presenters.
Thanks, Scott. So my name is Pradeep Lal. This particular program focuses on biodegradable additive print structures with decouplable interconnection, and that's the approach that we are taking for development of sustainable print processes. Focus is still on additive to be able to reduce e-waste reduction as a result of the life cycle of the product itself. And what we are hoping to be able to demonstrate is the end-of-life decoupling of the appropriate parts once the structure actually has fulfilled its operational use life. The intent also is to focus on low temperature processing for the reduction of the carbon footprint. So what we hope to be able to leverage is some of our prior work on flexible thin power sources that was conducted under PC 5.6, where we actually worked on state of health degradation under a number of stresses of daily motion that flexible hybrid electronics may be subjected to. We are currently working in PC 6.4 on low temperature processing, sub 100 C assembly methods for assembly of components and interconnects. And it's a combination of some of these aspects that we hope to be able to leverage to develop this sustainable solution. So specific capabilities that we want to seek, and we want to be, and this is more intended to be more inclusive of the various types of materials, developmental materials that may be in development, perhaps not proven, and readily available. We are seeking companies with biodegradable inks and dielectrics, for example, that could easily go into a landfill without really spoiling the groundwater quality or what have you. Separable interconnect solutions, we have some, but we'd like to see what others may be out there, and environmentally friendly power source solutions. Again, we have one that we have specifically identified, but we'd like to see what else may be out there. Thank you.
Thank you, Pradeep. All right. So now I believe we're going to the virtual presenters. Abhijit Dasgupta from the University of Maryland is up first.
Yeah, so this topic is on using additive methods for repair, field repair, of electronics that are degrading or have failed in the field. And the idea is to reduce the waste stream, that is, reuse electronics that would otherwise have been discarded, reduce the waste stream, also reduce the need for the manufacturing supply chain. So both incoming and outgoing footprints are reduced. The challenge, of course, is trying to ensure that these additive repairs are going to be reliable enough and functionally effective enough to work in conjunction with the original parts. So we had an award on a related topic in PC 6.2. You see that on the left half of the slide. And these are specifically for RF components. So we have been able to demonstrate that, yes, we can indeed conduct repairs that get us back up to a reasonably acceptable threshold of the original performance, and that, yes, they do degrade, the repairs do degrade with environmental life cycle. So in the field, the repaired parts will also degrade. We've started to quantify those and how the RF performance degrades with continued use. The question has come up is, okay, where's the underlying understanding of what the acceleration is of if we see the in-test degradation, how does that translate to field conditions? So in 7.3, we would like to continue that work and bring that level of fundamental physics-based understanding of how do we quantify these degradation rates and what does that mean in terms of field degradation rates of repaired electronics. Also, the kind of environments that we will consider, we want to expand that based on needs of several federal labs that we are working with. They want also mechanical environment, so uniaxial and multi-axial vibration, combined temperature and vibration, and also high G drop testing, and translate that to field conditions. So we have, in 6.2, we collaborated with Lockheed Martin Sustainment Group and with University of Binghamton. We are also open to new collaborations in 7.3. Thank you.
All right. Now I believe we're going to Grace Chen from UMass Lowell.
So I assume that you can see the slide. In this specific slide, I just want to highlight what UMass Lowell and my lab. So anyway, in this slide, I just want to highlight what UMass Lowell could offer in terms of the sustainability area. So in this slide, I put two different projects that we have worked on before. On your left-hand side, where we apply and design safer solvents for remanufacturing electronics. So in one of the projects, we designed a safer solvent to remove conformal coatings that is used in electronics. This will enable the repair and remanufacturing of some parts, especially like the parts used in electronics. So we were able to do that. We were also able to use the safer solvent systems to recover the plastics parts. So on your left-hand side, we showcase the solubility measurement system that we use. We also have the capacity to process and characterize biodegradable or recyclable or recycled materials. On your left-hand side, it shows where we use biodegradable polymer to produce thin films, and how we compound it and mix it with biomass to accelerate biodegradation. Beyond that, we also we have the Toxic Use Reduction Institute on campus, where it can facilitate the alternative assessment to evaluate the safety. So that's what I have on this slide, and I look forward to any potential discussion or collaboration in this regard. Thank you.
Thank you very much. All right. I believe next we're moving to topic 7.4, the manufacturing of soft and stretchable electronics. Our first presenter is in person, Elliot Gomez from UES.
Hey everyone, thank you so much. I'm excited to be out here today to talk to you about our material that we've been working really hard over the past year developing. It's called Element. It's a liquid metal-based ink, and we've been developing it for a lot of different printing paradigms, such as screen printing, blade coating. We're working on a few others. If you're interested, please let me know. The main advantage of Element is that it is a stretchable ink. We've been able to test our devices. You can see the stretchable USB device that we've been developing. We've tested it out to 100, almost 200% strain, and it works reliably. And so very minimal, low resistance changes when you stretch it, low hysteresis when you stretch it. There's no heat sintering. It's activated in other mechanisms. And so we're really looking for applications. One of the biggest challenges that we're looking for to team with is manufacturing. So how we've been able to develop some of the devices in the lab, but how do we scale it up? How do we manufacture it on a larger scale? And so this is what we're looking at going after. We're looking for some robust interconnect solutions, new printing techniques. So if you're interested, please let me know. I also have brought some devices, and so if you want to look at them, we've been able to put them on some wearable devices just to showcase some cabling solutions that can go in textiles. So it's a fun material to work with, and so let us know if you're interested, and we'd be happy to talk.
All right, thank you, Elliot. And there have been a few of our presenters in person today who have some samples to show to anyone in the room who's interested. We have conference rooms at the back that are available for after this session is over for any of those kinds of discussions and looking at samples and things like that. All right, our next presenter is Kevin Turner from Upenn, also in person.
Great to see everyone in person. I'm presenting today to talk a little bit about our capabilities at University of Pennsylvania. We have interest in multiple topics, but I'm only presenting on one here. I'll mention a few at the end that we're also interested in, but particularly on 7.4, soft and stretchable electronics. We've been doing a lot of work in soft robotics, and a particular interest in soft robotics are materials and systems that can change their stiffness over several orders of magnitude, so you can go from soft to stiff. And we've been doing this through shape memory polymer materials. But in order to actuate these shape memory polymer materials and induce the change, you need to locally excite them, either electrically or thermally, and we believe FHE devices and FHE backplanes are an ideal way to do this. And so we've been working on approaches to use tunable stiffness materials for grasping, as you can see there, and manipulation of objects, but there are other applications of tunable stiffness soft robotics. So we're particularly interested in finding industry partners with an interest in soft robotics or similar tunable stiffness elements, say in aerospace or other applications. We'd also benefit from connections on the design side, particularly from the electrical engineering side. And then we're also interested in new printing processes for making these shape memory polymer structures. There are a couple animations. Is it possible to advance one or two? And one more too. So that's on topic 7.4. We're also happy to partner on other projects. Myself, I have core capabilities in my lab on the mechanics of flexible hybrid electronic devices. We have lots of techniques to measure the properties of interfaces, model the properties of interfaces from a mechanical standpoint, characterize reliability with nano indentation, other techniques. A lot of expertise in interfaces, bonding, wafer bonding, thermocompression bonding, things of that type. So with that in mind, we also have an interest in topic 7.1 if you're looking for expertise in these areas. And then I also want to highlight there's a larger team at Penn. We're a large university. There are about 10 faculty that are interested in opportunities at NextFlex. And one of them that's online is Flavia Vitali. She's in the School of Medicine and has developed really innovative dry electrodes for EEG, ECG, and EMG devices. So if you have an interest in topic 7.7, please come see me today, and I'd be happy to help connect you with Flavia, who's online. So my email and phone number are at the top. Taking John Williams' advice from a week ago, I include my phone number, so feel free to call and reach out, and I'd be happy to talk to you.
Thank you, Kevin. All right, I think that in 7.4 we have one more in-person presenter, Vincent Milove from Momentv. Excellent. The floor is yours.
Good morning, good afternoon, everyone. Momentv Performance Materials. You may know us formerly as GE Silicones. We are a formulator of silicone formulations. We are a global company based out of Waterford, New York. We do have decades of commercial aerospace defense materials with tons of legacy and flight heritage. We excel with materials in harsh environments, whether they are FDA approved or on the backside of a solar cell going to new solar systems. So, as you see here, my eye chart, what do you need a silicone to be? It can be almost anything, but really there are certain intrinsic properties of a silicone that we're going to work with. They can withstand those broad operating temperature range that are listed there and often in further extremities as well. They are able to be processed to be low volatility, low contamination, high purity. They do offer low shrinkage as well. We are able to modify the silicone polymer to change some of these properties, whether it's our refractive index matching for some of our optical bonding formulations, or through the use of a functional filler. It could be as simple as changing the rheology of the formulation, or to provide a electrically conductive or a thermally conductive, electrically insulated solution with formulations that have very low volume resistivity to EMI shielding or ESD applications depending on the functional filler package. So really our goal here is to speak to the FHE community, let you all know what tools are available to your material toolbox. You'll see here that we are able to bond to a variety of substrates, including Kapton. We have our application lab that I mentioned out of Waterford, New York, along with global resources available to us as well. And please note that, again, these materials are typically commercially available. We are working on our membership at this time, several hoops to jump through, but we are, like I mentioned, able to provide commercial off-the-shelf formulations. But as we push for membership, we do look forward to possibly innovating and doing R&D work to help fulfill your needs as well. Thank you all.
Thank you very much. All right. I believe we're next moving to topic 7.5, the enhanced dielectric materials and manufacturing methods for FHE devices. And Ahmed Bousnaina from Northeastern is up first.
Thank you, Scott. So this is we did not have that last year, so this is a new development. And so we're printing pattern down to, we can print these down to 2 micron or even smaller if needed. So these are dielectrics. You can print low K or high K dielectrics. So the one you see is about dielectric constant of 7, for example. Most of these are inorganic. We're focused on inorganic ones, specifically for capacitors, for gate dielectrics, for if you need any dielectric, if you're doing an inductor, for example, you need that. So this is a technology that's very similar. It can be cured using UV or temperature. So it can be cured at room temperature, and the electric constant is the same in both cases. We tested them for pinholes. It works very well. You can see we can pattern them in small scales. You can see these channels are 10 nanometers wide, for example. For example, they can be wider, they can be smaller. The thickness also can be controlled from 20, 30 nanometers all the way to a few microns or larger, for example. You can do it on a large area or a small area. So the nice thing about it is this is a high throughput technique. So I can do 4-inch by 4-inch in about a minute, 1 or 2 minutes. So it's a very high throughput technique, and it's room temperature, completely room temperature approach. And so we're looking for partners to help us integrate this into devices or components or encapsulation technology, because, like I said before, we don't really do circuit design. We like to work with partners that can actually provide that capability, as well as testing. We do testing, definitely. We have testing capability, but it's not as sophisticated, or we also need reliability testing, which we don't have. So we're looking to partner with anyone there who's interested in this. But this capability is new, and we work very hard on developing it, and we're ready to share the technology. Thank you.
All right, thank you, Ahmed. Our next presenter is virtual, Alkema Kurtlu from UMass Lowell.
So again, I'm Alkema Kurtlu from UMass Lowell. I mentioned in my previous slide that we are actually working on several in-house dielectric inks specifically for additive manufacturing and printed electronics applications for RF and microwave devices. What we have developed them for and have used them in include as planarizing layers. Everyone that has been involved in high frequency applications of any 3D printed parts knows that you have to deal with surface roughness, which can really deter your performance. So these planarizing layers, being able to fully control them and having the proper RF properties is extremely important. Insulating layers, whether you're working on a capacitor or other types of applications, as I showed before, in terms of integration. Gasket materials, again, I showed that before. You see the picture of it in the middle section of the slides. Again, in terms of using it to stabilize the performance of the resistive ink. So once you actually put this on our in-house resistive inks, and then you, let's say, sinter or heat that resistor, the values do not change due to the stabilizing ink. So that's a very important new development that we have. Working on the low loss aspect of dielectric inks, I was actually really happy to see this come up as one of the topics, because as all of us in this printed electronics world know, it's really hard to come by commercial dielectric inks, which have everything that you need in terms of, let's say, the viscosities, the losses, the dielectric losses, the mechanical properties. So this is the main reason that we've really gone into making these inks. So in terms of the future work that we've already been working on is taking our UV curable inks and making them higher DK. I mentioned we have another dielectric ink that goes up to about 50 for the real part of the dielectric, with less than 10 to the -2 for the loss tangent. Again, lowering losses for some of these that we use in actual RF performance devices. And then working further on these boron nitride nanocomposites, which you can see in the middle that we've used, especially for this gasket material. We do have patents on this. And just finally, I'll be happy to talk about these in more detail, but the last column shows a new UV ink we developed for aerosol jet printing, so you can get very controlled, spaces and line widths. But moreover, what we've seen is that we can actually utilize this ink to make a three-dimensional structure. So we call it like stack printing. It's done purely on the 2D aerosol jet, but we can get up to, and the middle picture shows what we call our little flower. It was made purely by the mechanical properties of this UV ink that was developed in-house. So we're looking for partners where there might be different ideas for applications. We do a lot of characterization, up to about 40 gigahertz in terms of the electrical characterization, as well as mechanical characterizations. So thank you very much.
Thanks, Hakim. All right, next is topic 7.6, manufacturing of FHE-enabled automotive components. We have one in-person presenter, Pradeep Lal. All right.
So this particular topic is on in-mold electronics for automotive. Specific applications that we are focusing on include HMI communications and lightweighting. And so we have a team that actually is formed, but we are looking for some additional capabilities. Specific scope of the topic is on additive print processes and component integration on thermoformed substrates. So that's basically what we are focusing on with those three applications, HMI, sensing, and communications as the end application. Looking for development of high yield process recipes for conductive traces and attachment of SMT components. So the center that I lead, CAVE 3, Center for Advanced Vehicle Extreme Environment Electronics, we have done a significant body of work on high temperature, sustained high temperature operation, high humidity operation, high G operation in the automotive underhood environment. And we hope to be able to leverage over 20 years of experience on development of various technologies for OBD, which is onboard diagnostics, ADAS, which is advanced driver assistance systems that you are starting to see in many of the platforms that exist today, and our prior work on constitutive behavior, characterization, modeling, and fine elements. Specific capabilities, we are looking for additional inks. We have a few that are compatible with thermoforming processes without degradation or with mitigated degradation. Solder and ECA companies that want to try materials in this particular platform or in this particular space, and automotive companies that have interest in risk mitigation in use of this new technology. Thank you.
All right, thank you, Pradeep. I believe next we're going to go to topic 7.7, the Wearable Human Monitoring Interface Demonstrator topic. And our first presenter is virtual, Wei Li from UT Austin.
So I'm proposing a wearable human attention monitoring device that can be used for a variety of applications, including battlefield, highway safety, and even learning enhancement in the classroom. The objective of the project is to design, fabricate, and demonstrate a low-cost wearable device using FHE tools and processes. So as you may know, soldiers in combat need to remain alert to make split-second decisions. Drowsy drivers on the road are causing 40,000 accident-related injuries and about 1,500 deaths annually. And sleep deprivation is, in general, is a decrease in human performances. So the wearable device we're proposing will monitor the human attention level through oscillographic signal. We have developed signal processing algorithms and detection algorithms based on a wearable sensor. So we have a sensor also developed. So this project we're proposing is trying to integrate the sensor signal processing unit and the computational unit on the same device. And also we want to include battery and and wireless communication unit on the same device, so that we can detect human drowsiness using cell phones, for example, a cell phone, and then the cell phone will be connected to cloud, and then cloud, you can monitor, soldier alertness or driver alertness through cloud. So we have ability to design the sensor attached to human skin, and we can also design the mechanical part to encapsulate the device, make a 3D printed mold for making large number of devices using molding. We're looking for expertise partners who can print the circuit and integrate the circuit for us. Thank you.
Excellent. Thank you very much. All right. On topic 7.8, this is our open topic for new program leads. Our first presenter, we have one presenter in person, Ahmed Husnain from Northeastern.
Thank you, Scott. So this is step beyond just printing the active components. So this is printing logic gate components, like you can see here, NOR, NAND, Inventor. Once you know how to print transistors, you can actually do all that stuff, And so we're hoping that this will be an addition to, instead of just adding passive and active components, you'll be adding logic components. And remember, this is, like I said, this is all printed. The metal can be at low temperature, not room temperature. The annealing or high temperature. If your interposer, for example, flexible interposer silicon, then high temperature is not an issue. But this is, again, the resolution can go down to 2 micron. We have the capability to go down to 0.6 micron over a large area. I'm not talking about E-beam here. And so you can do a variety of things. You can do decoders, you can do counters, flip-flops, a lot of things that you need for sensor boards or other types of applications. You can see a picture here on the wafer. This is just transistors, not the logic, but this is something that can be done. A variety of semiconductors. Typically, we prefer silicon, but you can do also other types of nanomaterials. The one thing I did not mention is that we have a fully automated tool that will do this. You can see it at the bottom there. This is fully automated, all software driven, clean environment, and the new generation actually will accept DXF and GDS files. So you put your files, and then it will print each layer, several layers, up to 5-6 layers, for example, and automatically. So this is the third generation that's in the works right now. But this is we're looking for partners that would help us take advantage of this and add more to the capability of additive manufacturing beyond just discrete components. We want to look for logics and then go even beyond that. But this can be very, very small. This is all micro scale, but can be really, really small depending on the need. Thank you.
All right, our next presenter is virtual, Dr. Jeremy Ward from Sentinel.
Thank you for the opportunity to share this, our story and our goals. My name is Jeremy Ward. I'm the Vice President of Products and Partnerships at Sentinel, a health and safety monitoring company that is being commercialized from an Air Force development program that aimed to enhance workforce safety monitoring. Between my previous role with the Air Force and my current role at Sentinel, I've always believed that FHE provides a great opportunity to seamlessly integrate products that are already being used in workplace environments to create a safer and more productive work environment. One set of environments that's well suited for these types of technologies are those that are inherently risky, often chemically or electrically volatile. There is, as you can see on the left, a selection of products. There are many others beyond this that are sufficiently mature to be demonstrated and tested and used in these environments. However, due to the lack of exposure of FHE to some of the safety and environmental test organizations, they are yet to be adopted and credentialed for use to these workers. We're proposing to risk reduce the industry adoption of FHE systems and components delivered from across various NextFlex members through enabling their assessment, testing, and potential certification for use in these high-risk occupational environments. We want to do so by bringing in safety certification or test organizations dedicated to safety certifications into the community as a part of the effort. We welcome partners with candidate technologies that have a pathway to enhancing workplace safety, as well as component providers that might find their components or their processes used in these types of settings. I invite you to scan the QR code, especially if you're virtual, to learn more about Sentinel and our mission to protect and prolong the lives of those at risk. And please feel free to reach out if there are any interests or questions in supporting this area.
All right, thank you very much, Jeremy. Our next presenter is also virtual, Jim Burnham from Silicon Valley CTE. Jim, can you hear us?
I can. So thank you. I did send a slide in. Does that get presented, or do I present that myself?
No, it's we have it on the screen here. It's just
gotcha.
time
There it
delay.
is. Yep. All right. So my name is Jim Burnham. I am a longtime supporter of NextFlex and been doing the Flex Factor program for a long time. And as an educator, I'm a teacher. I teach engineering, mechatronics, so mechanical engineering, electrical engineering, mash those together, you get fire-breathing robots. And I got this email last night just before I was going to bed, and I thought, oh, challenge accepted, and so I sent a thing in. But I guess my real focus here is, I think that all the different companies come up with great ideas. That's awesome, but I also love the program, the Flex Factor program, where students, high school students, get to really kind of dig into what FHEs are and how do they use them, but they don't really get to use them. And I know that NextFlex here local has been working on an Arduino-based FHE, and my proposal is to really take that to fruition and actually wrap curriculum around it, because there's too many times where someone has a really great product, but they're trying to get into the education space and they don't have curriculum, and teachers just don't have time for that, right? You have to be able to hand them, here's 2-week lesson plan with all the labs and everything. Here's a 4-week lesson plan, here's a 9-week lesson plan, and everything wrapped around it. And so my proposal is to move forward on getting an Arduino-based FHE built with some parameters to let it be connecting to a little edge connector with the flexible ribbon cable, and then be able to connect it to breadboards, and then let students be able to really kind of explore FHE at the same time when they're learning about an Arduino and C++ programming and basic electronics, and just kind of understanding the whole thing around FHEs. So mostly I was trolling my friends here at NextFlex here in San Jose, because I know they've been working on this Arduino, but I really think that this is a really valuable thing that I could lend a lot of expertise to, as far as building out that curriculum and creating those lesson plans, and creating a product that you could then turn around and just hand to high school or junior high or even college, junior college teachers, and just say, here is 2 weeks, 4 weeks, 9 weeks worth of curriculum. Thank you.
Fantastic, Jim. Thank you very much. And I will I hesitate to comment on as people are presenting, but what Jim was just saying there, we do have education and workforce development as a section in the proposal that is in our guideline. We suggest a short statement as the length for that portion of the proposal. And there's some additional language in the guidebook that explains that, it is typical for projects to involve, undergraduate and graduate researchers as part of the project execution. And so if that's what's going to be done as part of the education and workforce development, then just a brief statement is what's appropriate. But if a project were to, let's say, include development of curricula, to develop a course or something like that, that would certainly be beyond, the standard that's included in almost every project. And so that's where I would encourage you to expand, the content of your proposal to describe that education workforce development being an important part of the NextFlex mission. So I believe we skipped over a few presentations because the presenters were having technical or other difficulty connecting. So tag and track. Okay.
Hi. Okay. Yes. My name is Gary. I represent Tag and Track. I wanted to present to you guys today, I guess, our what our company does and what our objective is. We're essentially trying to make smart labels for logistics and tracking companies and distribution companies. We all know that there are very standard industrial trackers out there today, with very rigid form factors, and obviously we're, in NextFlex space, we're trying to expand the flexible hybrid electronics into more advanced technology aside from just simple Bluetooth technology. We're trying to now integrate cellular technology into the flexible hybrid space with our smart labels, and that we've actually already done prototypes with cellular Cat-M1 and NB-IoT technology on polyimide labels. And now we're currently working with NextFlex to try to integrate that into silver ink and PET process so that we can eventually scale up to a large-scale manufacturing process at very low cost. So our ultimate end goal is to work with a partner, a CMO, to be able to create these labels and print the circuitry and place these IC components on paper substrates with the eventual goal to be biodegradable as well. So our goal is really to be able to make these smart cellular labels on biodegradable material at low cost and high volume. So our progress has been that we've pretty much started. We've already got working prototypes on polyimide, and now we're moving on to next stage with PET, and eventually we want to get to the scaling phase of being able to produce on biodegradable material. That's kind of a little bit spiel about what we do, and I think that's pretty much it.
Right. Excellent. Thank you very much, Gary. And I understand that is going to be our last presenter. We had a couple of extra slides, but we haven't been able to connect with the submitters. So the whole point of this session has been to connect potential proposers with each other. And so we have a variety of ways that you can do that. For those of you who are virtual, you're already on the Whova platform that we're using to stream the event. You can find each other's contact information through that platform. You can also follow the link from any participant's contact information, bring it up, and there's an option that you can actually you can send messages back and forth through the platform. You can set up a video call through the platform with each other. Whether you choose to connect that way or offline, anything that works for you is perfectly fine. The other thing for the in-person audience to know, as I mentioned, several of you had little devices, demonstrators, samples, things like that to show. We can use the conference rooms at the back here as soon as this session wraps up to discuss. We allowed extra time, that way we wouldn't run out for these presentations. So we will be ending a bit early, it looks like. I'd encourage, if you haven't taken a fab tour recently, to avail yourself of a fab tour when the session is over. Lunch is going to be at 12:15 Pacific, so we have a bit of time before that. And we will be resuming the symposium with the first technical session at 2 o'clock Pacific, 5 o'clock Eastern. Apologies to those of you on the East Coast for whom that's going to be a bit late to be starting a session, but it's tough working on all 4 time zones. So, are we almost ready with the last slide?
Thank you. So this is about printing traces. You can see we're already doing flip chip. The top one, actually, that's a NextFlex design. The bottom one is a startup that does new IoT chips with very small pads. The pads that are under the chip is 40 micron by 40 micron, and they're looking to go 20 by 20, so that's really hard to do using wire bonding or using any other type of technology. And so, for example, for the one at the bottom there, that was actually 2 layers that because we can make them smaller, we made them in 1 layer. For example, we designed the fan-out pattern. So you can see some of them are thick. These are the power, and the other one is for data. And so this technology, again, it's the same process, can be used to do metal or do dielectric or do semiconductor. And although the metal and we've been working on that for a long time. So we have done silver, we have done copper, we have done gold, we have done platinum. The platinum basically was for NASA sensors that will go on the International Space Station. Copper also was done for a NASA project. So this technology, the nice thing about it is, like I said, throughput. It is automated, and the feature size, high resolution, ultra high resolution feature size that can go down to 2 to 5, and now we have the capability to go down to sub-micron. So we're certainly looking for to utilize that, especially for printing traces, especially for really small chips that try to use less real estate on the board, but because of the current wire bonding and the current basic trace printing, they can't, because they have to use a lot of area. So this one actually will allow you to do that, to shrink things even more. So we're looking for people to help us with design, because even the redesigning actually was not done by us, it was done by somebody else. So we're looking for testing. Definitely, we do some of our testing, but the long-term reliability testing and the in-field testing we don't have. So we're looking for on the application side and the circuit design side, as well as on the reliability testing and field testing. Thank you.
All right. Thank you, Ahmed. All right. So that concludes our teaming event presentations. I'd like to make a comment. I'm really pleased at the number of presentations that we've had, the variety of interests that everyone's expressed. Looking forward very much to seeing your proposals in not very many weeks, and certainly to talking with all of you about proposals during the pre-submission consultation phase that we're just kicking off here. Before we break, I'd like to introduce Dr. Art Wall, our Director of Fab Operations at NextFlex, who will say a few words, I believe, about the fab tours. And then we'll break for lunch, and we will resume at 2 o'clock Pacific with the first session of the symposium.